Okay, so functions with discontinuities. What we're actually looking at here, because a discontinuity could be a horizontal or vertical asymptote, but what we're looking at when we're talking about discontinuities for this unit is holes in the graph. Okay, so first thing, what we're going to do is quickly graph these functions here. So first one, the reason we're doing this is because a lot of the graphs will end up like this. So we're going to 4, we've got a slope of 1, so the graph's going to look something like that. Okay, here we've got a x plus 2, again, graph's going to be something, oh that's not right, better make sure I'm right, something like that. Okay, slope of 1 over 1, just going up. Now this one's a little bit harder, but we know that we've got our vertical asymptote at x equals -1. So we've moved this way 1. We've got a horizontal asymptote of 0. So our graph is going to look something like this. And again, this is just general shape, okay, not super important outside of those 2 points. So 2 points, general shape, throw our asymptotes on there. Okay, so there's our graphs. Those are very common graphs when we're looking at this, because a lot of the times you're not going to use the higher degrees because we just want to get across the point that you know when a discontinuity happens. Okay, so if I was looking at these graphs here, what we've done is we've actually given the table of values and we're going through and graphing. Okay, and you'll notice at x equals 1, we can't have a point there. Okay, the reason that we can't have a point is because the graph doesn't actually exist. But if we were to graph this, if we were to actually look at where this graph is, you're going to notice something, because on the top we can change this to x plus 4 and x minus 1. Now what actually happens is these two values cross out. So we have our x plus 4 graph, but at x equals 1, we don't have a point. So what this graph is going to look like is this. And what that hole means is that the graph doesn't actually exist at that point, because we've simplified the equation before. I'm not going to graph all of those table of value points. What we're going to look at though is the graph doesn't actually exist at that point. Same thing on the next one. We've got x plus 2, x minus 2, and then it's all over x minus 2. So I'll put that in brackets just to show you the cancel out. This graph's not going to exist at x equals 2. And we've left that point out of the table of values. It would slot in right here. So what's going to happen is we're going to have our graph, and we're going to get to 2. And so if I were to graph this, what I typically would do is put my y-intercept, and then I actually put my hole, and then I can connect those dots, which is, you're going to use a ruler, I'm just kind of freehanding it, and you're going to just graph the graph. Okay, you just don't go through the hole that you've created. Last one, on this one, we're actually canceling out the top with 2 of the bottoms. Okay, so this becomes 1 over x plus 1. Okay, and we've got a hole at -1. Okay, so if I were graphing this, we've got 1 over x plus 1, but we haven't actually gotten rid of the x plus 1 asymptote. So I guess we have a hole there, but really the graph's never going to exist there anyway, so it's still an asymptote because we haven't completely gotten rid of the bottom of this fraction that has that same cancel out. We canceled out a bunch of x plus 1s, but we didn't cancel them all out, so it's still an asymptote. So sometimes when you're looking at this, you have to recognize, is it a hole or is it still a vertical asymptote? So essentially what we're saying is, we've got some equation or some function that we're canceling out values on the top and the bottom. we need to cancel out all of the bottom values for it to be a whole. If we don't, like in that last example, it's still going to be an asymptote. Okay, so it still doesn't exist at that point. It's still a discontinuity, but it's no longer a hole in the graph. It's actually just an asymptote, and we can't have the graph exist at that point. So let's look at a couple examples. So the first one here, first thing you should start recognizing now is we need to factor any values just to check that. Okay, and that sometimes makes it hard for us to find our horizontal asymptotes because we want to look at the highest degree form and we need to look at the coefficients. But the equation's still there. You're never going to lose that first equation. You shouldn't be canceling it out or crossing it out. And it does, this is where it helps to write everything down. So here we've got x minus 3, and this is x minus 3 squared. So I'm actually going to just write it out like that. We'll cancel out one of our x minus 3's. We've got 1 over x minus 3. So what that means is we have a vertical asymptote at x equals 3. We've got a horizontal asymptote, and this is one that people forget a lot when they're stating it all at y equals 0. This can never equal 0 because we've got that 1 on the top. Okay, other than that, you could do domain, range, all of those things, but the important values are there, so I'm going to just graph this. We know our general shape. I've got x equals 3, we're not 0. It's y equals 0. We'll put that along there. And we've got our values. Okay. This is just the general. I guess we could do, we don't have any x-intercepts. We can do our y-intercept so that we know where that point crosses when we come across here, and we can label our graph a little more accurately. So our y-intercept is going to be -1/3. Okay, I'm just looking at that top equation, making all my x's 0. I get -3/9, and I reduced it. Okay, so this is -1/3. All right, and so we've got all of our points there. We've got our graph. It's nice and neat. Those are kind of the main things you need. If the degree on the top was higher, we do an oblique asymptote instead of a horizontal, but we've got everything we need. All right, the next one. So again, coming back to, do you know how to factor? Okay, so this is where factoring is getting important again. All right, so we've got our graph. We've got x plus 3, x minus 5, and then on the bottom, we're going to have what? X plus 3 and x plus 2. Oh, I should have written that back the other way. I'm going to just, the only reason I'm writing it the other way is so that it stays nice and neat, because those two will cancel out. Okay, so now what this means is, in the last one, if you looked at it, we didn't cancel all the x minus 3's from the bottom, so it wasn't a hole, it wasn't a discontinuity. Here, we've canceled all of the x plus 3's from the equation. So what that means is we have a hole at x equals -3. Then we've got a we've got a vertical asymptote at x equals -2. We've got a horizontal asymptote. We're going to look at our coefficients of our highest degree. We can look at our new equation because we've canceled stuff out at 1. And if you look at your original equation, you would still have it at 1. So let's put all those values on. So we've got -2. So x equals -2. We've got 1. Okay, we can actually sub in and find exactly the value of the hole. Okay, and the reason that's unique is that's going to tell us our domain and our range, because if it doesn't exist at x equals -3, it's also not going to exist at whatever the y value for that is. So what we're going to do is we're going to do f at -3, and I'm going to choose my new equation. It's just easier. So I'm going to have -3 minus 5 over -3 plus 2. So we're going to get -8 over -1. Okay, so -3 minus 5 is -8. -3 plus 2 is negative 1. So that's just going to be 8 over 1, which is just 8. So our hole is actually at negative 3 and 8. So then we can actually just put that point on the graph. We know that this is y equals 1. We know that we've got a hole at negative 3 and 8. So it's approximately right there. Okay, and now we can just kind of connect the graph. So our graph is going to be this and that. And where are x and y intercepts here? So x-intercept equals, what do we have, 5. And our y-intercept is equal to 15 over, or negative 15 over 6. And I'm not even going to, why not? We'll reduce it down to negative 5 over 2. It doesn't matter. You could have left it. So, we've got those values. So it's going to look something like that. And there's our graph. Now if I'm stating my domain and range, I need to remember that that hole is actually part of the domain. Okay? It's also part of the range. So our domain is from negative infinity to 3, and we're not including it. And then it's from 3, again not included, to, that's negative 3, to negative 2, not included again because that's an asymptote. And then we're going to go from 2, negative, to infinity. Now our range, we're going to do something similar. We're going to have negative infinity to 1, not including it, 1 to 8, and 8 to infinity. So we're including our asymptotes and our holes when we're looking at domain and range. All right, last one. So we've got something like this. We can factor this, so we're going to have x squared over x and x plus 5. So I'll go to a different color just so it's clear. So we're canceling that out with that. And we're back here, so we've got a hole at and that's going to become what, x equals 0. So that's going to be 0, 0 if I sub into my equation. Okay. So that would be, I'll just do it up here, f at 0. It's going to be 0 over 5, which is 0. So we've got a hole at 0, 0. We've got a vertical asymptote at x equals negative 5. We've got a horizontal asymptote at y equals 1. X-intercept. This one should be a little bit obvious because we have an x on the top. Our x-intercept is equal to what? What do we have here? 0. Y-intercept is going to be equal to 0 as well. But those zeros actually don't count because that's a hole. So we can't have an intercept there if the graph doesn't exist there. So now we're going to just start putting all of our stuff on the graph here. We've got x equals, oh, I'm on the wrong side. Let's try that again. We're over here. So x equals negative 5, y equals 1. We'd go through 0, 0, but that's a hole, so we don't go through it. Graph's going to go something like this. We're not going to do domain and range this time. And there is your graph. If you're ever confused on these graphs, you can use either a graphing calculator or something like Desmos to check your answers and see where you've gone wrong. The only issue is with a lot of those is the holes don't actually show up unless you click on the point. So you'd have to click on 0, 0 to see that it was a hole, and then you'd actually see the whole value. It would show up as a hole, but other than that, they do show you the general shape quite well.